Okay, today we're going to pick up where we left off. So you should have the same printed notes from before. We're just going to fill in the rest of the blanks today. We've talked about the metric system and metric conversions and derived units and base units. So today we're going to talk about measurement and why that's important and what that means for us. So we have accuracy and precision. Sorry, these are two words that get used incorrectly as far as science goes quite a bit, but they are not too complicated to understand. So accuracy refers to how close a measured value is to its accepted value. What that means is, let's say you have a target, it's how close that is to the target. Precision refers to how close one series of measurements are to one another. So you cannot have precision unless you have multiple measurements. We do talk about the precision of a measuring tool because it's that tool's ability to give us precise measurements, that tool's ability to have repeatable measurements that are all the same. So again, accuracy is how close you are to correct. Precision is how close you are to everything else. So if you think of it like a target, this arrow is accurate. It's right dead center in the bullseye, but there's only one of them, so it's just accurate. That's the bell. Precise but not accurate. These three are all grouped together, so they're very precise. So you did the same thing multiple times, but you're not very accurate. This is actually pretty good for science because if you're getting all of your data all in the same place, even if it's not accurate, all of your data is in the same place. So your experiment may be good, you just may have bad measurement error or bad measuring tools. Over here is what you really don't want. You do not want to have all of your data to be completely spread out and nowhere near the correct answer. But this is the ideal situation where you have everything that's right dead on target and all grouped together. You want to be accurate and precise. You want your measurements to all be relatively close together, and you want them to be relatively close to the correct value. So that is what accuracy and precision is. Now, error is defined as the difference between an experimental value and an accepted value. And all measurements, everything that we do in science, every measurement we ever take has error. So you're never going to have a perfectly, completely, totally 100% accurate measurement. Now, because of the way that we do things and the rounding off of numbers that we will do, you may sometimes come up with an answer that is 100%, has zero error in it. But in truth, that's all a matter of how we are taking our measurements. All measurements have error. The better you are, the less error they have. So this is a data table from a lab experiment. You'll see A 1.70, 1.69, 1.71. These are all really close to each other. They're all very, very close to 1.7. So these are very precise measurements. All right. If we say the accepted value is 1.59, these are very precise, but 1.7 and 1.5 are not really that close together when you're looking at all these numbers. 1.57 and 1.59 are pretty close to each other. They're only 2/100ths of a point apart. So those are pretty close to each other. Now, error is the difference between the experimental value and the accepted value. So here's my accepted value. Here is the experimental value. So 1.54, 1.59. So the difference is 0.05. So that's your error. Now it's down. This is 0.05 low. This is 0.01 high. So that's your error right there. So as I said, trial A, those are the most precise. It's a grouping of measurements that are all really close to each other. B is the average of all of these, and that is the most accurate. And that's something that you need to know, is that when we do multiple trials, we don't just use any single one. The reason we do multiple trials is so that we can get an average, because you'll see that your average is always going to be more accurate and be better than all of your measurements separately. So this average is always what we're going to be using when we use the data. So we collect a whole bunch of data, and then we average the data for our trials to get the best or to minimize our error as best as we can. So to show error, we use something called percent error, and the error equation is experimental value minus your accepted value. And your experimental value is the value you get while doing your experiment. It's what you measure. The accepted value for most things is something that you're going to look up. In this class, oftentimes our accepted value for things is going to come from the periodic table, which is right here behind me. So our accepted value is what has been accepted by science as the accurate, true value of things. So error equals accepted minus experimental. Now these vertical lines are absolute value bars. And as you should have learned in like 6th or 7th grade, I think, in your math class, absolute value is your distance from 0 on a number line. So your accepted value minus your experimental value. Sometimes your accepted value is larger than your experimental value, and so you get a positive answer. If your accepted value is smaller than your experimental value, then you're going to get a negative answer. But no matter what, we're going to always record our error as a positive number. So if it comes out negative, we're still going to record it as a positive number. Percent error expresses error as a percentage of the accepted value. So a percentage is a part divided by a whole. Alright, so I have my percent error is my error. Notice that this part here and this part here are the same thing. So it's my error divided by my accepted value times 100. Okay, so there's our thing. Percent error is our error divided by our accepted value times 100. So this is the percent error equation. I'm going to do some example problems for you here in a moment, and we will go on from there. So I'm going to talk to you now about proper measurement. Like I said, all measurement has error. So how do we take a proper measurement? The precision of a measurement is limited by the tool being used. So how repeatable your measurement is, how well you're able to take this measurement and then do it again. That is repeatability, that is your precision. That depends on the tool you're using. Your recorded measurement should always include all known digits plus one estimated digit. That's going to sound a little weird right now, but hopefully after doing this and you seeing some examples, it'll make a little bit sense. So if I'm looking at this ruler, it's measuring this rod here, and you have centimeters. So they've magnified this so you can see it a little bit better. But we know that this is 4 centimeters, 5 centimeters, and then each one of these tick marks is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 tick marks here. So each one of these is 0.1. Okay, so we know the tenths place. Okay, so our known digits are 5 because it is definitely past the 5, and 0.1, 0.2. It's definitely past the 0.2. So we know 5 centimeters and we know 0.2 centimeters, and you simply add these together. So 5.2. So we know 5.2 centimeters. Our measurement should always include all known digits plus one estimated digit, because you'll see here that the line, or showing where this is, it's actually past the 0.2. It's not on the 0.2, but it hasn't made it to the 0.3. So we're going to make a guess. Now here we've made a guess of 0.3. Now that guess is going to be somewhere between 0.1 and 0.9. Alright, so 0.01 and 0.09. So you make a guess. Now if you were to say that this was 5.23, adding all these together, that would be a correct measurement. If you said it was 5.22, that would also be a correct measurement. Or 5.24 could be a correct measurement. It's not as correct. I mean, you get better with your guess as time goes on. But you'll notice that each person is going to make that guess a little bit different. That's where your error is. Your estimated digit is your error. But this is a fairly precise tool as far as what we're going to be using stuff for. It's accurate to the tenths place, and the error is in the hundredths place, which means that this error is plus or minus a few hundredths of a centimeter. That's not bad. So we could be, off. We don't know what the exact accurate measurement actually is. This is a guess. We don't know that 3 is correct. That 3 is a guess. But again, it could be 5.21, 5.22, 5.23. All of those would be correct, but it is 5.2. These are known. So if you put 5.3, then you'd be wrong. 5.20 would mean that this line is exactly on that 2 tick mark. 0 means your guess is 0. So there is no guess. There's still a little bit of guess because there's still some error in the length of the width of these tick marks, but that's for a discussion for another time. So that is how we take proper measurement. I am now going to do a few more examples, show you some examples of that error calculation and percent error, and then you can go on to your assignment. All right, so we're going to start off by doing a example of a percent error calculation here. So in lab, we measure the density of a material to be 39.6 grams per cubic centimeter. After lab, we look up the accepted value and find it to be 40.9 grams per cubic centimeter. What is our percent error? So the percent error equation, your percent error is your absolute value of your accepted value minus your experimental value divided by the accepted value times 100%. So again, these vertical lines are an absolute value. So I'm going to take this, and my accepted value is right here. It's 40.09. So I have 40.9, not 09, 40.9. And all the units are going to be the same. So I'm going to leave them off because they're all going to cancel out anyway. So I have 40.9 minus 39.6 absolute value divided by my accepted value again, which is 40.9, and then times 100. Now, we need to make sure that we follow the order of operations. So, order of operations, the PEMDAS. So we're going to do our parentheses first. These absolute value bars act like parentheses, so we're going to do it first. So 40.9 minus 39.6 is 1.3. So I have 1.3. Absolute value of 1.3 is 1.3. So 1.3 divided by, and I'm going to move this over here so we can see it. So I have 1.3 divided by my accepted value of 40.9. So take my 1.3 and divide that by 40.9, and I get 0.03178 blah 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 blah. Alright, so I'm not done yet though, because I haven't multiplied by 100. So I did the top here, I divided, and now I have to multiply by 100. So times 100. And that gives me a final percent error of 3.1. Now, this is 3.178. So that 8 is going to make that 7 round up to an 8. So 3.18. Again, I want you to round things to 2 decimal places. And since it is a percentage, we are going to put the percent symbol as our unit. So 3.18%. That is our percent error for this problem. All right, so hopefully that's not too incredibly complicated. It's just a few steps, but it's not very complicated math. Okay, so now we're going to practice looking at this measurement stuff again. And you'll notice that I have here a drawing of a meter stick, or it's in centimeters, so a centimeter measurer, and an object that we're measuring.
So you'll notice here, though, the first thing you need to look at is what the tick marks on your measuring device are. So we have only tick marks at the 1 centimeter interval. That's it. We don't have anything between them. So all we know is the ones place. So we know what's written on here. So we know when we come up here that 20 is known, okay? But it's not exactly on the 20, it's a little bit past the 20, but it hasn't quite made it to 21. So we're gonna make a guess. Now, experience tells you how to make that guess. Some guesses are better than others. Now, would I be technically correct if I said 20.1? Yes, because it is greater than that. But if you just said 20, you would be wrong because it's obviously past the 20. So I have to make that guess. The best guess would be, it's not exactly in the middle, but 20.4 would be a good guess for that one. You could say 20.5 or 20.6 would be okay, but 20.3. What you don't want is to have anything after that. I can't say 20.45 because that would say that that 4 is known. I don't know. So anytime you're looking at a measurement, your guess is always that last digit. That is the guess. And you must always include your guess when you're making a measurement for it to be a correct measurement from a scientific standpoint. So we know this, we guessed that. So I have a 0.4 is our estimate. So our guess is in the tenths place. We know the ones place, the guess is in the tenths place. So we're going to do a couple more examples, and hopefully this will make sense when we're through. Now for this one, I'm using the same measuring device, and it's a different object. It's slightly shorter now. The last one was 20.4. This one, you'll notice though, it's exactly on that 19. It's right there, right on it. So we know the 19, and it's exactly on the 19. So what's my guess? I still have to have the guess. That's the thing. If I just put 19, when you have just 19, that would suggest that this is our guess, because your last digit in a measurement is always the guess. If you just write 19, then that means your ones place is a guess. Am I guessing on that ones place? No, I'm not. My guess is not the 19, so that is wrong. So we don't want that. What we know is the 19. So we want to guess after that, but it's exactly on the 19. So that means my guess is simply 0. So I would write 19.0. That tells me that my guess is still in the tenths place. So when you look at this, this is accurate to 1 centimeter. So it's accurate to the ones place. That's its accuracy. It's accurate to the ones place. So the guess is in the tenths place. So it's accurate to the ones place, the guess is in the tenths place. That's what you need to know when you look at this. So any measurement I make with this tool should always have 1 decimal place, because I'm going to be making a guess in that 1 decimal place. Okay? Now, different tools have different levels of accuracy. I realize that I'm using a meter stick here, and we're not going to use meter sticks hardly ever in chemistry. However, they're easier to draw, and so that's what I'm using for my examples. You measure with graduated cylinders and triple beam balances. You make the measurement the same way. It's just, you're using a different tool. So let's do a couple more examples. Okay, so for this one, you'll notice our measuring tool has changed a little bit. Now we have our 1, 4, or 3, 4, 5, and there's more tick marks here. So I'm going to look at this differently. Now, first, I want to see what our accuracy is. We know the ones place. We know the tenths place. So that means our guess is going to be in the hundredths place this time. So we know the ones and we know the tenths. Those are marked on our tool, so we know those. So that means we're going to have a guess in the 100ths place. So every measurement we take with this tool should look like this. Now, if it went on to have 10, 15, 20 on our meter stick here, then you can also have stuff over here. But this last digit is what we care about here as far as our accuracy and our precision go. We know the tenths place. Our guess is our hundredths place. So when we look at this measuring tool, we know the 4, okay, because that's here. We haven't made it to the 5, so we know the 4. And then this is 1, 2, 3, 4, 5, 6, 7. We know the 7. Notice it doesn't quite make it to the 8, so we know the 7. And so we have to make a guess. Now, you could guess anything. A lot of you are going to be tempted to just say 5 because, well, in the middle it must be 5, right? But it's obviously past halfway. If it was right halfway, 5 would be a good guess. It's obviously past halfway. It's not quite there. So I would say 4.77. And then we have our unit of centimeters. Now, if you said 4.78, you'd be correct. If you said 4.76, you'd be correct. If you said 4.75, I'd still give you credit for it. Heck, if you said 4.71, I would probably still give you credit for it. The important thing is that the 4 and the 7 must be correct, and then your guess is your guess. Some guesses are better than others, so it's always good to try and make sure that you make a good, accurate guess. And now that you have seen a couple of examples drawn on the whiteboard and worked out that way, now you're going to see a couple using actual chemistry equipment. We're going to do an example with the triple beam balance and an example with a graduated cylinder for how to make those measurements properly and make your guess and how to use those pieces of equipment. So watch those last two and then you're on to your assignment for today.
Hey guys, so I want to show y'all how to use one of our triple beam balances today. So right over here I have one of our actual triple beam balances, and so today I am going to show you how to get the mass of Mr. Kern's keys. So I'm going to go ahead and put that on, and then you'll notice we have 3 different sliders, one in for the hundreds, the tens, and the ones, and further. So the first one you always want to work with is the 100 slot because it's your largest. So always get that figured out first. And so I'll slide it one at a time until I get too far. So this obviously went too much, went too far, so I gotta back it up a step. And then the next, I'll go the next smallest, which is our tens. And so I'll go a little bit at a time until I finally go too far. And yet again, I gotta back it up. And so now I gotta get to the last slider, the smallest one. So this is where you get your final numbers from. And so I'm just going to slide it over a little bit at a time. And you got to wait for it to kind of balance out sometimes to see where it's going to be at. So I'm still got a little too much, so I got to keep backing it up. And so that's almost straight on balance. So when these 2 lines are meeting, that's when you know your object is balanced. And so then you can add up your sliders. So the first one, I have 100. Whoops, shouldn't push that down. So I have 100 plus 30 plus this slider, which is past the 4. So I have 134. But then these little tick marks are what's going to be in your decimal place. And so I'm going to come take a look at this, and I got to look at it straight on. So it's past the first tick mark, so that's 0.1. But then we always have an estimation digit. And so that's always the next digit over. And so this one looks like it's barely past 0.1. So I think it looks like it's about 0.11. So my grand total would be 134.11. And that's how y'all use the triple beam balance.
All right, so today we're going to learn how to read a graduated cylinder correctly for a chemistry class. So right here I have a beaker filled with some water with blue food coloring in it. And I want you to notice that beakers do have lines for measurement on them, but we don't use those because beakers are not very accurate. They're not made for accuracy. They're just made to give you a general idea. So they're just used to take chemicals from one container to another, or one location to another. We don't actually use the beaker to actually measure stuff. That's what graduated cylinders are for. So I'm going to take, and I just want to measure some in here. So I'm going to pour some of my water into the graduated cylinder. And then let it set. I'm going to add just a little bit more just because I feel like having more fun. All right, so I want to try and get the bubbles out. And then the first step for making sure that you measure in a graduated cylinder correctly is to make sure that your eyes and this level of the water are as close to level as possible. So I'm actually going to get down lower to where my eyes are right behind it so I can see it. Now, I can't really see the numbers because they're facing you, so I'm going to turn it around real quick so I can see it. We have, it's a little bit above the 20 there, okay? So back to here, you see that, let's look at these measurements though. This is 20 and this is 25. And so we have the big lines are 1, 2, 3, 4, 5. So each one of these big lines is 1. So this would be 20, 21, 22, 23, 24, 25. So the little lines here in between would be the half milliliter lines. And those are just kind of as a guide to help you make your guess properly. They don't show the precision of the tool. Now, next thing I want you to look at is I'm going to move it to where the numbers are out of the way a little bit. And hopefully on the camera you can see that there's the top of the water, but then the water kind of curves down. And that curve is called the meniscus. When you're reading a graduated cylinder, the meniscus is what you look at. Never look at the top line where it touches the glass. You're always looking at the middle where that meniscus is the lowest. So if I make it to where I can look at it, I have 20 and it's not quite to the 1. And so it's 20.4 because it's not quite to the 5. It's a little bit below that 0.5 mark, so it's 20.4. And that's how you measure with a graduated cylinder.